Okay, so how's polymerization made in the case of these reactive unsaturated molecules? So initiation here relies on a radical. So here's an R dot, where R is generally some carbon fragment, or in your textbook, I think refers to the OH radical as being used here. But even things like the benzene molecule can be used. So here's a C6H5 dot, can be the identity of R dot. And what's really important here is that we recognize that the radical, that is the unpaired electron, which is given symbol dot, ends up transferred to the first mer in the chain. So here's ethylene. A reaction occurs to generate a single bond to that mer, and the reactivity of the radical has been transformed to the end here. So we see a radical end group that is reactive here, and we've inherited that reactivity from the initiator R dot. That is the first step, called initiation. Propagation is going to have similar ideas in that we need to inherit that reactivity again. That radical end group must be found again. But propagation means we take the product of a previous step and add mers to it. Okay, so here's an ethylene mer. And we see that the first propagation step involves that product from the initiation step, making a new bond to that new mer there. And so that's our first propagation step, and we've inherited that radical again. Second propagation step would extend that even further. So we would expect now to just add another mer there. And so to show that quickly, just draw that. We're going to draw that radical so we don't forget about it. And this would be the next propagation step. The next one would be even further and further still. Okay, so this is the most dominant reaction that happens in addition chain polymerization of these unsaturated monomers, and it's the reaction that builds the molecular weight often very quickly into perhaps even 1 million molecular weight in some cases. Termination has two options. The termination reaction can go by disproportionation or combination. Okay, so note to isolate these from one another, I'll simply break it apart like this. So in the combination termination reaction, two chains, okay, so these could be quite long, have their reactive radical end groups come together and make a single bond at the middle. Okay, so I'll highlight that here. This new single bond right there has reacted from these two radical sites coming together. Radicals are, of course, unpaired single electrons, and if we pair them up, we can make a carbon-carbon single bond. That is, of course, a 2-electron sigma bond. Okay, so a polymer here with, molecular weight A, if you want, perhaps similar to molecular weight A here has come together to react with that partner. And here the molecular weight here would be near double that, 2A, for example. And so combination termination doubles the molecular weight of the reagents that were used, the propagating chains. Okay. Disproportionation is the more difficult termination reaction to understand. The main idea is hinted at in its name. There will be a disproportionate set of products here that occur from the disproportionation reaction. Okay, so we will see that the disproportionation reaction leads to two products where there has been one has lost a hydrogen. We show that here. And the other polymer has abstracted that hydrogen to gain it, and that is now shown here. Okay, so in a sense, because most polymers undergo this termination reaction after many propagation steps, the chain ends are the chain lengths are very long. The molecular weights are nearly the same. The slight abstraction and impact of moving a 1 AMU hydrogen from one molecule to another doesn't really impact the molecular weight significantly. And so disproportionation reaction doesn't change the molecular weight, but it does remove the reactivity from the molecule. So regardless of the disproportionation or the combination termination reactions, neither of them no longer have the radical end groups needed to propagate. So at this point, the chains are termed dead, and termination is the result. Okay, so the mechanisms there can be used to explain many of the polymers you might be familiar with: polyethylene, polyvinyl chloride, polytetrafluoroethylene. These all come from these carbon-carbon unsaturated monomers that come together and make the polymers. So here's the monomer for polytetrafluoroethylene. And notice that the repeat units are shown here, whereas if we wanted to show the polymer structure, we would have to use our parentheses and show all the same chemical species within it, similar formula to the repeat unit and of course to the monomer unit in this case. Okay, polystyrene is similar. That comes from the monomer that is styrene. So here, carbon-carbon double bond again, but now a C6H5 ring, that is the aromatic benzene ring, is the appendage. And so I'm showing that to help you recognize what this detail here is. Okay, so there's the styrene monomer becoming the repeat unit for polystyrene shown in that top entry. Polymethyl methacrylate is commonly used in plexiglass, and so we'll note here that we have an ester side chain. And then down below in bakelite, one of the earliest synthetic polymers known, involves that benzene ring again. I'm abbreviating here with a circle to indicate aromaticity and shifting of the double bonds in the ring. Here's the phenol molecule. This combines with formaldehyde, shown here separate as a separate molecule, and the formaldehyde is responsible for giving us CH2 bridges, and therefore by inspection of the product repeating unit we can install CH2 bridges at 3 sites: the 2 flanking positions to the OH group or directly across it. So this is a highly covalently cross-linked polymer material that involves potentially 3 covalent linkages at each repeat unit. It becomes very difficult to draw a nice, clean, linear representation of that chemical structure like we have been doing for polyethylene. Okay, so to elaborate on that, here's some of the details. So here's the formaldehyde molecule atop, and we have 2 phenol molecules below to show a detail of this reaction. This clearly involves a different mechanism, no longer using radicals, but we are going to generate a driving force to polymerization by eliminating a small molecule. So this step growth polymerization is the polymerization that involves individual chemical reaction between pairs of reactive molecules. The pairs of reactive molecules here are a formaldehyde with phenol. Those are the pairs of molecules needed for this phenol formaldehyde bakelite polymer. Okay, and so there's our 2 phenols. What's highlighted here in green is the hint at what the elimination product will be, so what small molecule will be eliminated. As you can predict here, we're expecting water to be the byproduct, and so if this is a heated reaction, often this water will be boiled out of the reactor to drive the reaction to completion, or perhaps even drying reagents can be used to capture it. So in this example here, we can clearly see how the formaldehyde is responsible for giving us the bridging CH2 units. This is only one of the two. We might expect a similar reaction here and here, even here and even here. And so we can build molecular weight very, very quickly given how many reactive groups there are at the phenol site. Okay, because we've eliminated water, and you might expect an appropriate term for that could be a condensation byproduct. This step growth polymerization is also known as a condensation